Hello everyone, this is module M5.1, the first module of Unit 5. This last unit will be a short one. We're going to briefly survey some ideas in modern physics, and then we're going to cover nuclear physics in a bit more depth, since nuclear physics is generally regarded as the most applicable to health sciences. The 17th and 18th centuries witnessed a revolution in science that accompanied similar revolutions in religion and society during that time. Copernicus, Galileo, and Descartes all contributed to the steady progression of physics enlightenment. James Joule made huge advancements in heat and energy. This revolution continued through the 19th century, when Weber, Hertz, Faraday, Ohm, Gauss, Ampere, and Maxwell contributed to the development and consolidation of what at the time was a cutting-edge discovery, electricity. All of this led to a growing sense that humanity had achieved the pinnacle of knowledge about the physical world. During this time, methods became more mathematical and comprehensive, and less philosophical. Madame Marie-Anne Lavoisier was instrumental in turning chemistry away from alchemy and superstition, and played a major role in establishing what we know today as the scientific method. In particular, Isaac Newton's breakthroughs in mechanics and his laws of motion were among the most important advances in physics of all time. The period of time from roughly 1700 to 1900 Common Era is called the classical era of physics, and the concepts and techniques developed during this time are referred to as classical physics. Because Isaac Newton was one of, if not the, most prominent physicist and mathematician of the classical era, this era is also commonly referred to as the Newtonian era. In 1900, British physicist Lord Kelvin is said to have proclaimed, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." But Kelvin was a bit premature on this count, because cracks had already started to form in the core of classical physics. The wave nature of light, conflicting with Newton's particle theory of light, was proposed in 1801, and somehow, both theories, particle and wave, seemed to be correct. In 1898, Madame Marie Curie had discovered two new radioactive elements which could not be explained by any classical theory. And in the same year that Kelvin made this infamous announcement that there was no new physics to be discovered, Planck proposed the radical new idea that the energy of light is confined to small, discrete amounts, called quanta. Einstein's theory of relativity soon followed, and one after the other, classical ideas were proven to be mere human-scale approximations of the more accurate theories of relativity and quantum mechanics. As you may have guessed from all the famous classical names matching the units that we've been using throughout the semester, most of what you learned in 1510 and 1520 comes from the classical era, and for good reason. Classical physics still does a very good job of describing physics at ordinary human scales, the scales at which the classical experiments were generally carried out. For example, the difference between the calculation of the moon's orbit around the Earth using Newtonian physics is just 1.3 centimeters different than the same calculation using relativity. So Newtonian physics is good enough to send a rocket to the moon. However, at scales much bigger than Earth's orbit, or very, very small scales at about the size of an atom, Newtonian physics starts to fail. For example, we have seen that light behaves as both a wave and a particle at subatomic scales, which goes against classical understanding of waves and particles being distinct entities. On the larger scale, minor deviations from Newtonian gravity can be detected in the orbits of Mercury and, to a lesser extent, Venus. Modern physics encompasses ideas and concepts of the last century and a half that radically changed our understanding of the fundamental laws of the universe. In the classical worldview, physical processes play out against a constant background of space and time. Time flows at a constant, predictable rate, and space provides a firm, immutable coordinate axis to fix precisely where and when events occur in relation to each other. Physical processes flow like a recipe, with results that can be fully predicted so long as the initial conditions are precisely known. In the non-classical, modern worldview, space and time themselves bend and warp, and the results of any physical process can only be determined with some probability. Interestingly, Maxwell's laws in their full form are consistent with both relativity and quantum mechanics, despite having been formulated during the classical era based on classical ideas and experiments. This is part of the reason that physicists hold Maxwell in such high regard. At the smallest, most fundamental level, physical processes do not have a constant outcome. Rather, a given physical process may have any number of possible outcomes, each associated with some probability. If the process happens enough, outcomes with higher probabilities start to dominate. As systems become larger and more complicated, the probabilities start to average out. By the time processes reach about the scale of an atom, many processes essentially only have one statistically likely outcome. Thus, larger, more complex systems on the human scale or larger tend to show few, if any, quantum effects, even though quantum properties within these systems are still happening all the time. On the other end of the scale, relativity predicts that large masses can actually bend space and time. So black holes and large objects in space experience the warping of space-time. But since we humans are for the most part stuck on Earth, which has a constant gravitational field that overwhelms the gravitational field of any of our human-scale objects, we do not see much space-time bending going on. Relativity also predicts that space and time will be measured differently for objects moving with respect to one another. In one famous relativity problem known as the twin paradox, one twin takes a spaceship and flies to another planet, traveling at about 70% of the speed of light, or about 470 million miles per hour. Once this twin reaches the planet, she lands, turns around, and returns home. The twin who stays on Earth thinks that her sister was gone for 25 years, but the twin who traveled at such a high speed, called a relativistic speed, only clocks the trip at 18 years due to the bending of space-time caused by her high speed. However, at Earth-only scales, such relativistic effects are minimal. For example, an airplane that takes off and travels 600 miles per hour for 8 hours before landing again will experience the trip as taking about 0.4 microseconds less than somebody who times the trip from the ground. This is hardly enough relativistic distortion to worry about on your next airplane ride. In Unit 5, we will focus on nuclear physics because it is the most relevant to health sciences. We will see probabilistic quantum effects when we look at decay rates and half-lives. Relativity comes into play in nuclear physics when we look at the very deep inner workings of nuclei, but for our purposes, we won't be doing any relativistic calculations. I might be biased since I am a particle physicist, but I like to start with the very smallest, most fundamental building blocks and work up from there. You don't have to memorize these particles, but many of them will be mentioned in the next few modules, so I think it will be very helpful for you to be familiar with a few key ideas from particle physics. The most complete description of physics that we have today is called the Standard Model of Particle Physics, and these are the particles that make up the theory. These particles are believed to be fundamental, meaning that there are no even smaller particles that make them up. The largest group of fundamental particles are the matter particles. These are the particles that make up all the stuff around us. You are made of matter particles, quarks and leptons. Matter particles are collectively referred to as fermions. The other two groups of particles are called bosons. There are two types of bosons. Gauge or vector bosons are called force carrier particles because they are directly associated with the forces that govern physical processes. We have already seen that light can act as a particle or a wave. When it is a particle, we called it a photon. When it is a wave, it carries the electromagnetic field, which can create an electric or magnetic force on another particle. So in a sense, the photon is a particle and a force. In particle physics, where Newtonian physics is all wrong and quantum mechanics makes the rules, what you're used to calling a force is actually a quantum entity that can behave as either a particle or a wave. There are four fundamental forces in nature: the strong force, the weak force, the electromagnetic force, and gravity. Hopefully, you are pretty familiar with the electromagnetic force already. Any particle that has charge, either positive or negative, can be affected by the electromagnetic force. When an electromagnetic interaction occurs between two particles, the electromagnetic force takes the form of a photon to carry the force through the interaction. The strong force is mostly seen inside the nuclei of atoms. The strong force carrier is called the gluon, named because it is so strongly attractive that it holds protons and neutrons together in the nucleus like a sort of glue. Unlike electric charge, which can be positive or negative, the strong force has 3 possible charges. To keep track of these charges, physicists often refer to them as colors: red, blue, and green. although of course the charges don't have actual optical colors that you can see. We just needed words to describe the interaction, and using color words was convenient. The strong force is only felt by quarks and gluons. None of the other particles feel it. Anytime a strong force interaction occurs, it is a gluon that carries that force. The weak force is also seen in subatomic interactions. As its name implies, it is very weak. This means that usually the weak force is drowned out by the much stronger electromagnetic and strong forces. One important thing the weak force can do that none of the other forces can do is change a particle from one type to another. So the weak force can take a single top quark and turn it into a bottom quark, an up quark, and a down quark. Or it could take a muon and turn that into an electron and two neutrinos. So the best place to look for the weak force is in processes where particles change type. We will see the weak force when we talk about a type of nuclear decay called beta decay. The weak force is carried by the Z and W bosons. All the matter particles can interact via the weak force. Physicists have often theorized about another force carrier they call the graviton, which should carry the gravitational force. But if it exists, nobody has been able to discover it yet, and it is not included in the standard model of particle physics. You could think of force carrier particles as having a special handshake. The photon doesn't know the secret handshake for color, so it can't interact via the strong force. But it does know the secret handshake for charge, so it can interact with any other particle that knows the secret handshake for charge. The second type of boson is the scalar boson, and as far as we know, only one scalar boson exists. The Higgs boson doesn't carry any forces, although it can interact with other particles through either the electromagnetic force or the weak force. The Higgs particle itself does not actually contribute to the matter that makes up you and me and all the objects that we see around us. But it is still very important because one of the quantum effects of the Higgs boson is to give all the matter particles, or fermions, their mass. This function is so important that the Higgs particle is often called the God particle. So the Higgs particle interacts with any of the particles that have mass, including the Z and the W bosons, with one exception. We're not sure if the Higgs particle interacts with neutrinos. We used to think that neutrinos were massless, so the Higgs particle would have no reason to interact with them, but we now know that neutrinos have very, very tiny masses, about a millionth of the mass of an electron. Where do neutrinos get their mass from? We don't know if they get it from the Higgs boson or if they even interact with the Higgs boson. This is one of the unsolved mysteries of particle physics. Most of the matter we see around us is made up of just three types of matter particles: up quarks, down quarks, and electrons. You may notice a few peculiar things about the way these particles are described. First, their mass is often given in units of mega electron volts over c squared. This is an odd way to put units together that we will see a lot of over the next week. Electron volts are a way to describe energy, so you can see that mass equals energy over c squared just comes from Einstein's famous equation, E equals mc squared. So using MeV over c squared as a basic unit for particle and nuclear physics masses makes it easier to take relativistic effects into account when needed. Every matter particle also has an antimatter particle. Antimatter particles are identical to matter particles in every way except that they have opposite charge. So an anti-electron has a charge of +1e. Anti-electrons are actually common enough that they have their own name, the positron. Gluons, photons, the Z boson, and the Higgs have no charge, so they are their own antiparticle. The W bosons have a charge of either plus or minus 1, so we say that the W plus is the antiparticle of the W minus, and vice versa. Neutrinos are also neutral, but we have not yet confirmed whether or not neutrinos act like their own antiparticle or not. It seems like they should, but in science we can't just say this is the way it should be. We have to prove it. And since neutrinos have no electric charge, and they only interact with the weak and gravitational forces, and their mass is so tiny that their interaction through gravity is almost imperceptible, they are very difficult to study. And many of the unsolved mysteries of modern physics have something to do with neutrinos. So what happens when particles and antimatter particles collide? Well, they annihilate each other, creating energy in the form of one of the force carrier particles, gluons, photons, Z or W bosons. The energy created by a particle and an antiparticle colliding is equal to the combined masses of the two particles times c squared. You can also create new pairs of particles and their antiparticles. To do this, you have to provide enough energy, also using E equals mc squared, to ensure that both particles can be created. Here is a summary of the 4 fundamental forces of nature. This chart compares the strength of each force to the strength of the strong force. So the strong force has been assigned a strength of 1. You already have a good feel for gravity and the electromagnetic force, as these were the primary forces studied in 1510 and 1520. Both the electromagnetic force and gravity get weaker with distance. You can see that the electromagnetic force is 1/137th as strong as the strong force. Gravity is actually even weaker than the weak force, and by a lot. It takes a lot of mass to create a little bit of gravity, which is why you can't just use the force of gravity to attract your cell phone to your hand from across the table. However, the electromagnetic force only affects charged objects, and since most objects are neutrally charged, humans still experience gravity on a daily basis much more often than electromagnetism. As mentioned before, the strong force holds neutrons and protons together in atomic nuclei. It is much, much stronger than the electromagnetic force or any of the forces, which explains why a nucleus can have many protons packed very close together and not blow apart due to the repulsion of so many positive charges. In fact, the strong force actually gets stronger as distance increases. If 2 quarks get too far away from each other, the potential energy in the strong force gets so strong that it is actually cheaper to create 2 new quarks via E equals mc squared and let them part ways as pairs than it is to continue trying to just pull 2 quarks apart. So the effective range of the strong force is only about 10 femtometers, because at distances larger than that, the 2 particles that are being pulled apart will simply break away and create a new, closer partner to interact with instead. This is why human scale interactions are not completely dominated by the strong force. The weak force is actually stronger than gravity, but it has a very small scale. We talked about the force carrier particles acting like both waves that carry a force and as particles. Well, more massive particles have a harder time behaving like a wave. So the weak force, which is mediated by the massive Z and W bosons, is very short range. They can't act like a wave and carry forces over long distances. The gluon and the photon are massless, so they have no problem acting as waves. But the gluon range is limited because new quarks will be created before the gluon has to act on a very large distance. So this leaves the electromagnetic force and gravity, which have no restrictions on their range other than that they can get weaker with distance. Now that we are familiar with the fundamental particles and forces, let's start building some matter. In nuclear physics, the primary particles we will work with are protons, neutrons, electrons, photons, and neutrinos. Electrons, neutrinos, and photons are fundamental, but protons and neutrons are not. So let's see what they're made of. Protons and neutrons are actually a chaotic mess of quarks, crashing into each other, annihilating and producing new particle pairs. This gob of quark soup is held together by the strong force, which is carried by gluons, represented by the squiggly lines on the picture. Each proton or neutron is a very complicated whirlwind of constant strong force interactions between the quarks and the gluons. And exactly how protons and neutrons behave at this particle level is a very difficult field of study where many things are still not well understood. However, as I mentioned earlier, in quantum physics, laws are based on probabilities which start to average out as you get to larger scales. So if we don't need to know exactly what is going on inside the proton or neutron, we can just take the average composition of the proton or neutron and just use that as a good approximation. On average, the proton contains 2 up quarks and 1 down quark. The net composition of a neutron, on average, is 2 down quarks and 1 up quark. So if you have taken chemistry, you may know that electrons in the outer shells that are free to interact with other atoms are sometimes called valence electrons. Similarly, the 3 quarks that make up the average composition of a proton or a neutron are sometimes called valence quarks. Atoms are built out of protons and neutrons. The simplest atom is a hydrogen atom, which is really just a proton. Since a proton is made up of 2 up quarks and a down quark, its charge is 2/3 E plus 2/3 E plus -1/3 E equals +1 E. This is why protons will usually attract a single electron with charge -1e that will orbit around the proton. Could we build an atom out of just a single neutron? Actually, the answer is no. It turns out that neutrons are unstable. If a single neutron hangs out all by itself, it will turn into a proton after about 15 minutes. This happens because one of the neutron's down quarks will turn into an up quark via the weak force, emitting an electron and a neutrino. Luckily, when a neutron is busy interacting with other protons and neutrons inside a bigger nucleus, it is stabilized enough that it doesn't decay. This is a good thing because all of chemistry and biology depend on most atoms being relatively stable. The universe would be a mess if neutrons decayed after only 15 minutes inside of an atom. However, we will find out that many times neutrons do still decay into protons even within an atom. This is called beta decay, and we will cover it later. Usually in nuclear physics, instead of writing out the whole process at the quark level, beta decay is simply written N goes to P plus E plus nu. We may not be able to create atoms out of just neutrons, but antimatter is still a thing, and yes, we can create anti-atoms. In fact, at a particle accelerator in Illinois, we used to create trillions of antiprotons every single day and smash them against regular protons just to see what happened. Of course, if you get too much antimatter, it'll start annihilating with matter until nothing is left, so we don't see a whole lot of antimatter interactions in nature. As far as we know, there is a lot more matter in the universe than there is antimatter, which is why the universe hasn't just canceled itself out yet. But nobody knows why there is more matter than antimatter. This is just another great unsolved mystery of modern physics. We can keep adding protons and neutrons to build bigger atoms, relying on the strong force to hold atoms together despite the repulsion of all the positively charged protons. The core of an atom without any electrons is called the nucleus of the atom. The electrons that are attracted to the nucleus due to the protons are not as tightly bound to the atom. This is because the electrons do not experience the strong force. They are attracted to the protons just from the electromagnetic force, which is weaker. With enough energy or force, electrons can jump between atoms, and the number of electrons surrounding any given nucleus can therefore change. When the number of protons equals the number of electrons, the atom is electrically neutral. But when the number of protons is greater than or less than the number of electrons, the atom is said to be ionized. The number of protons dictates the main properties of the nucleus as a whole. The number of protons in an atom is called the atomic number and is denoted with a capital Z. In fact, chemicals are sorted by their atomic number, even if they have different numbers of neutrons. The number of neutrons is denoted with a capital N. This chart shows stable nuclei up to about 85 protons. We talked about how the electromagnetic repulsion of the positively charged protons is counteracted by the strong force to hold the nucleus together. As the nucleus gets bigger, the protons and neutrons on the outer parts of the nucleus get further apart, beyond the range of the strong force. In order to increase the amount of strong force holding the nucleus together, without also increasing the electromagnetic repulsion between protons, larger nuclei tend to have more neutrons than protons. My favorite element is copper, which has 29 protons. According to this plot, copper can be stable with either 34 or 36 neutrons. Look at the element with 50 protons. That is tin. There are 10 versions of the tin atom that are stable, more than any other element. When an element can have different numbers of neutrons, the different versions of that element are called isotopes. So copper has two stable isotopes, one with 34 neutrons and one with 36 neutrons. Tin, which always has 50 protons, has 10 stable isotopes, with 62, 64, 65, 66, 67, 68, 69, 70, 72, and 74 neutrons. The number of neutrons plus the number of protons is denoted A, which is called the mass number. An isotope is often called by the name of the element and its mass number. So for example, the two stable isotopes of copper are copper-63 and copper-65. Both chemistry and nuclear physics need a clear and concise way to note how many protons and neutrons a given isotope has. Isotopic notation is a common method. To find the number of neutrons, N, you just subtract Z from A. So the number of neutrons in copper-63 is 63 minus 29 equals 34. Often, nuclear physicists will refer to both protons and neutrons as nucleons. So mass number A is the number of nucleons in the nucleus of an atom. When you see an element on the periodic table of elements, you often see it written something like this. Notice that this does not give the total number of neutrons. This is because on the periodic table, this square represents all the isotopes of copper. The number 63.546 represents the average mass of all the known isotopes of copper, given in atomic mass units or AMUs. One atomic mass unit is 1/12 the mass of an atom of carbon-12, which is the most common stable isotope of carbon. Hopefully you now have a better understanding of how nuclei are put together and the basic terminology we'll use to talk about them. In the next module, we will look at the properties of atomic nuclei in a bit more depth. In this module, we gave an introduction to modern physics and then started talking about the basic concepts we will use in nuclear physics. We learned that there are 4 fundamental forces of nature: the strong force, the electromagnetic force, the weak force, and the gravitational force. Nuclear physics involves interactions via the strong, weak, and electromagnetic forces. At the nuclear scale, gravity is too weak to be noticeable. The most important fundamental particles in nuclear physics are the up and down quarks, which make up neutrons and protons, and the electron, the photon, and neutrinos. The stability of the nucleus depends on the balance between the strong force, which holds neutrons and protons together, and the electromagnetic force, which makes the protons repel each other. A particular combination of neutrons and protons is called an isotope. The number of protons is denoted Z, the atomic number, and the number of nucleons, which is the number of protons plus neutrons, is denoted A, the mass number. The number of neutrons is denoted N. An atom that has more electrons than protons, or more protons than electrons, is called an ion and is said to be ionized.